Hi, and welcome to today's lecture on deep learning and neural networks. Today we'll look into like the first technique on how to make smaller models, because on the one hand the models get bigger and bigger and bigger because that improves performance, but of course comes with a cost that they might not be applicable anymore in some devices. So yeah, today we'll cover one technique, which is knowledge distillation, and then on Thursday we'll look into another technique called quantization. But before we're doing that, we should also talk about the evaluation. So first of all, thanks for everybody filling out the evaluation form. That was very helpful. I'm happy that a big majority of you seems to be quite happy with the course. That's of course always nice to hear. There were also, of course, some suggestions what to do better. We are looking into that. They are not, I mean, I didn't find one big thing which is repeated over and over again. There were some things which contradict each other, and that's normal. I mean, some say it's too much content, sometimes say it's too few content. That is normal, but there's also other suggestions. I'll try to look into that, especially also from other classes, that you can't understand the slides without listening to me. That is intentional, I have to admit, because during the presentation, that should give you some hints, but you should also listen to me. So I tried not to put the full text always on the slides, because for presentation, I feel that is not so helpful. I can understand that that is, of course, also a bit of disadvantage if you try to learn with them. I don't have a good solution for that yet. I have to admit what to do differently. If you have great ideas, always also feel free to just talk with me. I'm happy to get any feedback on that. I'll try to look into what to do different, but I don't, as I said, have the best solution yet. If there's anything else, of course, it's good to get this feedback once in the semester, but if you have other feedbacks, feel free to talk to me after the lectures also. Good. If there's any more questions from your side, any complaints, you can do that now, or you can, as I said, come to me and I'll try to address them. Good. So what is the motivation for our work today? So on the one hand, these models get really bigger and bigger and bigger. This is only over like 5 years. And you see on the y-side, the number of parameters is in the logarithmic scale. And you see that they're increasing significantly, and they will even increasing further. And it's a bit not going that fast at the moment. We have decent numbers around something like, on the one hand, the small models on around 7 billion, the big model on maybe 70 billion. But we see that this is a very nice thing of neural networks, especially in machine learning. You can get better by just making bigger models. This is, of course, on the one hand, really great, because it's a very easy thing to make your models better. On the other hand, it comes with a cost. And that means like generating some output with each of these models gets more and more expensive. And it's even getting more difficult if you think about where you want to apply the models. I mean, the one thing where they are applied is in the cloud, in large computational centers, where, of course, you can have big models. But even there, it's a problem because it's costly. I mean, the more GPUs you need per request, the more it costs. And you see that by now, like applied models even get a bit smaller again. It's even more challenging if you think about that you want to apply your models also in many other devices. Maybe we want to have more and more AI working directly on the phone, for example, for privacy reasons. I mean, maybe not all of you want that everything gets sent to some cloud service, but you want to have enough parts of your AI assistant running directly on your mobile phone or directly on your personal robot. And then, of course, it's getting even more challenging because there you have limited computation capacity, you have limited memory capacity, and furthermore, I mean, you also should, I mean, even if you can do large calculations, you shouldn't do this too much because normally they are all run without permanent power supply. So the more calculations they are, the more power consumption we have. And yeah, we want that these models, yeah, working well without like running for all these points. So we see there is like somehow a trade-off, and which should be addressed. That on the one hand, we want to have large models for performance, and on the other hand, we want to have small models for computation. And this is exactly the aim we're addressing in this week is how can we build the strongest models on small hardware. So you can do that in two ways. You can either fix your hardware and say, what is the best model I can get there? Or you can fix your performance and say, oh, for this performance, how can I minimize the hardware requirements of that? And well, yeah, there are, of course, different techniques of doing that. And today we'll focus on one, which is called knowledge distillation. So the idea is to a better small model by getting information from a large model. But before we are talking about the technique, the first question is, what do we mean by a limited computation, by small hardware? In which phases do we want to have limited hardware? And which trade-offs do we dare take into account? So what does it even mean that we have, yeah, somehow limited computation? Because that is essential to address what techniques you will, because they're all not like doing limited hardware for everything, but it may be on different phases. So the first important question is, where do you have constraints? Are you interested in speeding up your training, or are you more interested in speeding up your testing? And of course, it depends a bit on your use cases. So, for example, one big difference is the bit in research and in industry. So, if you're writing your master thesis, or your bachelor thesis, what you mostly will do is you train different models and you will evaluate them. So you always train a model, you test it, and then you go for the next model and test it again. Which means for training, you need to typically process a lot of data, and then testing. I mean, you need, of course, by now, hopefully you know that you need a decent amount of test data, but compared to how much training data that is somehow fixed. Which means most of your time you're spending is on training training. So you're really interested in having an implementation which is somehow efficient on training, because there is where you spend all your time. And maybe you can wait 1 or 2 days for your experiment to be trained and to evaluate. But if you always have to wait 2 weeks before you can get any results, it might get tied with your master thesis, because you just can do a very limited number of experiments. Of course, it's a bit also going, I mean, it's not completely not in industry. I mean, if you think about training a large language model, it takes a lot of time. We're more talking about months and so on. And then, of course, efficiency also gets very important. However, like in industry, of course, it's a bit different. Like a lot of cases, you once built a model, you have this idea found from the literature, you built a model, and then, of course, you not only want to run it once on your test data, but that's where you want to make your money with. So you want to apply it, and a lot of people should use it. So in this case, you're a lot more interested in the testing or in the inference phase, and you want to be efficient during inference. And to be efficient during training is therefore less important. And for example, today what we are mainly focusing is a technique which will be efficient in testing, because we are building a smaller model out of a bigger model. But of course, for training, it's even less efficient, because you first train your big model and then you train your small model. So it's additional work. But if you have this type of scenario where most of your footprint comes from from testing, that is, of course, essential. So this is like the first big question. Where are you interested in? Are you want to optimize your training, or are you optimize your testing? Of course, sometimes it's possible to do both, but in a lot of cases, the techniques either improve the one idea or they improve the other idea. The next question is then, what do you mean with efficiency? So what are the resources that you're needing? Do you want to apply your system on a CPU, or do you want to apply your model on a GPU? I mean, of course, you might do different optimization techniques depending on your techniques. We already learned that also like memory access is important, and we saw some implementation, if you remember, like Mamba or like the flash attention, where they optimize also for memory. So what is the bottleneck? So what do you really want to have to address in order to be efficient? And you see that people really focus on that. So this is for machine translation, where they look like how many 1,000 words can they do per second, and then how good is your quality. So on the y-axis here is the quality. So what you want to get is like somewhere on the top right. You want to have a high quality, but you want to have many words per second. And so these are somehow, of course, then the best systems because they have a high quality score, but also a high efficiency. And then it's, of course, a bit your decision. Do you prefer this system, or do you prefer this system? I mean, if you have a trade-off between two things, of course, you have manually decide what are your trade-off criteria and what is more important, a bit less quality or a bit less training data. Another question between resources is the data availability. So how do you process your data? There's, for example, if you can process your data in batches, so you not get a single input, but you always get like 20 or many, then you can do like parallel processing. You can also do like you do in training, where we talked about batches. You can also do batches in inference. And we learned that this is, of course, efficient or helpful when we think of like GPU usage. So you're a lot more efficient when you're not processing one example by another, but you're processing several examples at all. However, it might not always be possible. If you have more like the streaming scenario where input is coming in, let it be a film, let it be a text or so, or audio, you have to process it and then the output, then you cannot wait for the whole document, but you directly have to process. So in this case, you cannot do this type of batch processing, but you have to do the processing like one by one. And then again, are different conditions. So it might be that, for example, in the first one, a GPU is like preferable, while in the second, a CPU is preferable. And then, of course, the last thing you should consider is like the implementation. For all algorithms, there is like efficient implementation and non-efficient implementation. And it's not always that people like want to do an inefficient algorithm. It can be that the algorithm is inefficient, but therefore it's easier to adapt things and try new things. So when you think about your master thesis project and you want to do that, it might not be the only choice that you look at I'll start with the most fast implementation. If this implementation is very much optimized, it might be very hard to change this and do your interesting research on that. So that means there is, again, like some type of trade-off. Do I want to use a fast implementation, which therefore might be hard to understandable, or do I use a bit slower? Of course, it's not always the case. It can also be that they're both as easy or as complicated, but differently fast implemented. So, which trade-offs do you have to think of when building these models? So if it's about memory and throughput, for example, a very easy thing to do is like to make your model like more efficient is to increase your batch size. We saw that if you have a large batch size, you can better parallelize and so on. However, you also learn that you have to store more information at once. You have to store the whole batch, and that means your model will have need more memory. So you need less calculation, but more memory. So normally you have both that can be part in the inference, can also be in training. You have to do somehow there the trade-off. So what is the maximum memory I can use in order then to get the best possible like computation thing? These are all like now things you have to consider without taking into account the real technique. Of course, the other thing is like the quality versus throughput. Like if you have larger models, you have a better quality. And so there is normally an easy way to improve your throughput by having a lower quality, or improve your quality by just having less throughput. So you just double your model size, or you halve your model size. What we want now to address today is, can we also like shift this line? If you think about this line, you have like quality and throughput correlation. And then with one fixed architecture, you have different points there. Of course, they're not linearly, but you should see some degradation. The larger the model is, the better your quality is. And now you want to see, can we, for a fixed, model size, can we improve the performance? Or for like a given performance, can we reach the same performance with less computation? And that will be somehow the aim of the techniques we are looking into today. Before we are now going for the technique, any questions to the general setup we're addressing here? Okay, so the idea that we want to address here is what is referred to as knowledge distillation. So the idea is we are training one, or we have one large model, either we get it from somewhere, we're training out ourselves, and now we want to build a second model, which is a lot smaller, which naturally would mean that we have a lower performance. We might still have a lower performance, but the idea is now, can we get a higher performance when we also use a large model as somehow extracting the knowledge, distilling the knowledge from the large model and putting it into the smaller model? So can we extract this knowledge there and put it into the smaller model? We'll also often refer to the student-teacher setup. Again, the idea is, can we use a large model as a teacher that teaches the smaller model, the student model, what to do? And hopefully this should be then better than just training small models out of the box from the beginning. So it's a like an idea of like model compression, where the small model tries to mimic the large model. So the small model should like to pretend or like learn what the large model will do, and hopefully do similar things or so. And hopefully this is a stronger training signal than like just the signal from the training data we have. And we'll try to look and motivate it at least a bit, why, yeah, this signal could be helpful and could be stronger than just using a standard model and training it on the data. So of course, this is somehow the baseline. So you just train a small model. I mean, that you all could do. And we would expect that you'll have a smaller, like a lower performance. The question is now, when we have access to the large model, can we get better? Can the large model like tell us a bit what to do? And then it's easier to do that. This is like, yeah, quite well known already. It was first proposed in something like 2006 and then generalized. This is a paper you most often will find by Hinton in 2015 about like student-teacher models. So again, the student-teacher setup, where you have a strong model which tells you what to do. So the training setting is a bit like this. So we are having our input. Here we are getting our input, and now we have two models. We have our teacher network. That is a strong, large model which we have trained for a long time, which gives us really good performance. You can think of that of large language models, you know, like ChatGPT or Llama, or like also vision models. And now you want to train a small model that we'll refer to as a student network, which is more efficient, which we can put on your mobile phone, or you can run on your home PC, and it should perform very, very similar. And first we'll look at the default case. Let's assume both of them are just classification tasks. That is like the easiest thing we have normally for neural networks. So both of them for the input will give us like a classification over some classes. It can be like an image classification. It can be some type of NLP classification or so. So we just have output probabilities of our training network here, and we have the output probabilities of the student network. And normally, what would we do with in the standard case? How would we train the student network? What will we do with our output probabilities here? Yes? Yeah, before we're doing gradient descent. And what are we doing in the loss? To what do we compare it? Not know output probabilities normally, but to the data. Yes, exactly. So we take it to, we're comparing it to the gold labels here. Now we want to do something similar. Well, we want to not compare it to the output probabilities, but to the labels, but we want to somehow also compare it to the teacher network. So it's not that we read from a book what is the correct answer, but we believe our strong teacher network, which tells us what is the correct answer is. So what we need to do is we need to do what is referred to as the distillation loss. So we want to somehow compare the output probabilities and the two output probabilities of these two networks and calculate some type of loss. And we'll generally refer to that as distillation loss. And one way of thinking of it is we have two output probabilities here. And we'll see that one of these losses is motivated by the Kubrick library divergence. This is like a measure of measuring the difference between two probability distributions. And that's exactly what we want to do here. So we have two probability distributions. The one is from the student network, the other is from the teacher network, saying how probable the different outputs are. And now we want to make them as similar as possible. So the best case is if they do both the same prediction. If they have the same output probabilities, it means if they are predicting the same thing, then we can really throw away the large teacher network and just use the smaller student network because it does exactly the same. How is this Kubrick library divergence defined? So as I said, it measures the difference from one probability distribution to another. So mathematically, we just have to once look at that. So imagine you have two probability distributions. So we are taking the easy case here, the discrete. So you have maybe 5 outputs, possible outputs, and then you have a distribution. So 5 values, which are all between 0 and 1, and which sum up to 1, saying how probable each output is. That's the one distribution P, and Q is the same. So it has, of course, to be defined on the same space. An important thing. So if we're doing this, we're always assuming we have exactly the same targets here. So if we would do different targets, things would get at least more complicated. But I mean, since we want to have the student network to somehow do the same task as the large network, it's not a bad assumption that they should have somehow the same. If you are doing classification into cats and dogs with the other, you also want that the student network does classification into cats and dogs. And then you see, you just sum up over all possible outcomes here. So over all possible values, so cats and dogs or any other animal, you take the probability of P times the log probability of P divided through Q of X. You can view that if you now have it more in machine learning or in information theory, this is the information gain that you would have if you would use the original P instead of Q. So it's, again, maybe some of you remember some this information theory by Shannon. So you have some information in your probability, signal, and this is like the information gain you have when you use P instead of Q. One important thing is, I mean, often people talk about the QBRAC library distance. It's very important if you use this in somewhere that this is not like mathematically a distance. An important definition of a mathematical distance is that the distance between P and Q is the same as the distance between Q and P. So in Euclidean space, it's clear if you walk from A to B, it's the same distance as if you walk from B to A. If you walk from Karlsruhe to Stuttgart, the distance from Karlsruhe to Stuttgart is the same as from Stuttgart to Karlsruhe. In this case, it's not. So if you there replace Q and P, you'll have a different value. So it measures you how much gain you have, but it's not a distance. It's still an important measure, and we'll see that we can easily optimize to minimize this, and which makes, of course, no sense. We want to have them as similar as possible, but it's not that the similarity is measured in the same way. So the overall setup is then a bit more complicated. So we already knew that we can have easily several losses. We have done that several times before. And of course, in knowledge distillation, it is also helpful to have several losses. Because if we have our input and we have our outputs, so we are training anyway on supervised data, then of course it somehow makes sense to also take the classification loss in. So if we know this is the correct answer, we should of course use that also, and not only trust on the teacher, which is an AI system and also might make sometimes errors. So therefore typically in knowledge distillation, you're not taking only one of these losses, but you're combining both losses. Has one disadvantage. Does anybody remember what is the challenge when having several losses? Yes?
How you weight them?
Yes, exactly. So you have to have some good prior experiments set up, which tells you how to weight both of them. But still, it's normally good to get feedback from more symbols and use them all for them. However, there's still one open question. We have the gold labels, so we know what the correct answer is. So we can train the model to train the correct answer. So why should it be helpful to have even this other loss? So why is it helpful to also know what the teacher network? I mean, the teacher network can have the same prediction, then it's not clear what is the gain, or it can have another one, then the teacher network is wrong and it's maybe not better to learn it. So why should we take this into account and also try to make these losses the same? Does anybody have an idea? Yes?
Maybe when we find a global maximum or something, then the teacher network already has a very really, of course not the most global, but really good part of a really good local maximum. And then we can prevent that the student network will fall into very, very flat hits or something, or very small hills. You know,
Yes. So this is
the global maximum.
I mean, not to the global, but I mean to the one found by the teacher network. That's more like the machine learning or like the theoretical view of it. Maybe another one.
Maybe the teacher network already learned some kind of generalization effect of the training data. So if the data is a little noisy, the pseudo network can instead learn the generalization from the teacher.
That is one important point. Yes. So the noisiness. That is definitely correct. There's one more. I mean, that just some more ideas. Yeah.
Because we use those data, we use this same data set to first train the teacher network, which is a very big network. That means we have a lot of data. If we just use those data to train a central network, this will result in some overfitting, I think.
No, normally you have overfitting when you have too few data. It might be that it's underfitting, but this is the model cannot get more complex. Yeah. So overfitting is, I mean, the student and teacher could have, but this knowledge distillation typically doesn't have doesn't prevent too much what you typically have as overfitting. It's doing, that is right, and that's maybe like related to the first point. So in that way, it's correct. It's like doing some type of regularization, going to that to the correct one. But yes, it also was right that the noise is one important part, which is the thing. So that is even like the first point here. So data even naturally is noisy, even if it's not wrong. So if you think about text, I'll always take text examples again. If you think about training a machine translation system, there is not one correct answer. I mean, if you say good morning, you can translate it to guten Morgen or the hello or so. And if you like take a large data set, you have all of that. What is now happening in training is exactly as you said, you once learned it should be guten Morgen. And then the next case, you learn that it's hello and everything else is wrong. And that's how the CE, cross entropy losses, if you remember, if you're trained normally, you say this is the correct solution and all the others are the wrong solution. So what that means is if we're now normally training and we have these possible solutions, you have the ambiguity in there or the noise, that for the same input, we might have different output. This is like somehow giving very training signals in different directions, and that might not be beneficial. Of course, this is a lot nicer if we're now doing the teacher network. The teacher network is deterministic. For the same input, we always get the same output, and that's therefore like we have more clear signal and it's easier to use. So there is even like for some models, people first use a teacher network to generate artificial labels. We'll come to that as, I mean, that is the relation a bit to data augmentation. So you use a teacher network to just generate artificial labels for everything. And then you train on this synthetic data, which means the big advantage is that this is now no longer ambiguous. For the same input, you always have the same output, and there's not this type of noise. So it's easier to learn that. And what is the best, or the generalization, as you said, is already done there. This is like one important motivation. The other important motivation is that the training data is not really fine-grained. So typically what we get is this is a correct solution, and we only get this signal. So you only get the one signal. This is correct, and all the others are wrong. If you have a machine translation that says this is a correct translation, and all other sentences are bad. It's not telling you how bad they are, and maybe some might be still reasonable. If you translate good morning to hello, that is a decent, good translation, but it will say it's as wrong as Karlsruhe, which of course, yeah, is maybe not that helpful. If you think about information retrieval, it's similar. In information retrieval, I mean, you have a lot of documents, you have a query, and then you need to find what is the best matching. If you have training data, you have the one or like the 5 correct answers, but for all the others, they should then be wrong, but maybe some are also quite good. So you don't get this fine-grained signal how good the answers are. You only have, if you remember, the one hot representation of the correct answer, say typically this is correct and all the other is wrong. And that, of course, might make the learning a lot harder, while a teacher network might have a more generalized view, not only telling you this is right and this is wrong, but also how good these are. This is a major motivation for the student-teacher setting, is that the big difference is the student doesn't get labels, doesn't say correct or wrong, but it gives you a full probability distribution. And there's, of course, a lot more information in a probability distribution or a smooth probability distribution in some way than the probability distribution, which is 1 at one position and 0 at all the others. So for the other one, you get information, oh, this is good. The others might still be okay, but not perfect. And others are really bad, which have a low probability. In the default setup, we only have this one extreme. This is correct, and all the others are wrong. Which of course makes then learning a lot more harder. So that motivates why it might be beneficial to use the teacher network, because they can tell you already, okay, this is a good way of going, and helping you in that way. Okay, so how can we do knowledge distillation? So the first idea is, I mean, the first important thing, what is your baseline? It's always good what you have to be better. Important thing, your baseline is really training your student network on just the classification laws. So if you want to have a good idea, you should be better than this, because this is like somehow what you always can do. The other important thing here about the baseline is your teacher network is not your baseline. Typically, you will be never as good as your teacher network. There are some exceptions. We later come. You can try to have similar size student and teacher network. Then you might get also even better than your teacher network. But by default, if you think about the standard case where the teacher network is large and the student network is small, you will perform worse than the teacher, and that is fine. The question is, are you better than just training the student network, and hopefully can you come as near as possible to the teacher's performance? And then there's different ways of how you can like do this knowledge distillation. The most common way why we motivated just before, that's a response-based knowledge distillation. So you want to like extract the knowledge, like the response knowledge from the network. So you want to know what was the response by the teacher network, and you try to pretend to get the same, or like try to imitate the teacher and give the same responses. In this case, you only really look at the output probabilities. That has a big advantage. You're not really interested in how the student network looks like and how the teacher network looks like. So these can be completely different architectures. It can be that the one is a transformer and the other one is a state space model or anything. You're not doing any assumption. The only assumption I had before, so what is important, what has to be the same? Yes? Yeah, the classification, yes. So the output dimension, so the number of classes you have. I mean, you might have ideas of how to do it differently, but let's assume, I mean, that makes things easy, that we have exactly the same output probabilities here. But of course, it's also maybe a bit of a, I mean, it's a stronger signal. We just learned than just taking the labels. However, you're not really looking into the teacher network and what it has learned in between there. So that might also be important information, like how the teacher network looks. And therefore, there is additional ways of doing that. So there is a feature-based knowledge distillation, where you not only try to imitate the output probabilities, but you try to also imitate somewhere internal features that the network has learned. So like that some of the activations in some layers are similar. Of course, you can't, I mean, then you have to do some type of assumption. So now no longer the student network and the teacher network are completely independent of each other. Typically, you assume that the general structure is similar, that maybe there's more layers or smaller layers or so. But I mean, somehow you need to have somehow a mapping between the student and the teacher network to like measure at some positions how similar the features of these two networks are. Because if they're completely independent, then this doesn't make any sense. A last thing we'll shortly look at the end, and one example is relation-based knowledge. So that, I mean, if the network learns something between like layer 1 and layer 5 or something like that, some relations there, if the teacher networks learns this relation, we maybe want to learn similar relations also by the student network. So that you're not directly comparing, the main idea is you're not directly comparing different features like layers, like layer 5 to layer 3 or something like that. But you're trying to analyze what happens between layer 3 and layer 5 in the one network, and then say, oh, a similar thing should happen also between other layers in the student network. Good. Before we are now looking into these three, any questions about the setup? Yes?
Do this setup with the same network as teacher and as student?
We'll come to that at the very end, but yes, there is work on that. Of course, typically then gains get a little bit smaller. And the question is it then really worth it training two network? I mean, you double your training time, because you first train the first and then the second. But there is works like that, even doing that over several iterations and hopefully always getting better. That's a lot. I mean, maybe you have very limited training data, then you want to really make the most of your training data, then that, for example, might be a good idea to do. Okay, so let's start with a response-based knowledge. So the teacher's response is the output of the last layer. So the probability distribution over all your labels. We are first assuming, and the idea is we want to directly mimic this by the student network. So we want to achieve that the student network has exactly the same, or as similar as possible as least the same probability distribution there. So the question is then, how do we measure the distance? So you have the one probability distribution, you have the other. How can you now create a loss which tries to directly do this? Any direct suggestions? Doing that? Yes?
Could just use something like cosine loss, just replacing the one-hot labels with the prediction in the future.
Yes, so that is even like the most common thing. So maybe as a short repetition. So what was a cross entropy loss? So when we had a multi-class problem, we had the one-hot representation of the labels. So where one is 1 and all the others are 0, then we have the softmax output. And then the cross entropy loss was the label here, the label times the logarithm of the output probability, which is, the normal cross entropy thing. And as you correctly said, we can now replace here our label, which is, I mean, also you can view the one-hot representation as a probability distribution because it's like 1 at one position and 0 at all the others. We can replace that by the output. Of course, the calculation gets a little bit more inefficient than on the calculation, because for the normal cross entropy, the nice thing is that we didn't need to calculate the sum. Well, because if one value is 1 and all the others are 0, we can just only select the one and don't have to sum up, really calculate the sum. This is, of course, no longer be possible in knowledge distillation then, because we don't have this one. But what we have is, so what we are doing then, so we have now two output probabilities. Once we have the teacher's output, where each output is maybe Ti, and then we have together as a probability distribution, so that the probability of Xi is Ti, and the same is for the student network. And now you see the only difference is that we here replace our label by our teacher probability, or we can also put it as a more probabilistic view, the sum over the probability for the input given by the probability distribution P times logarithm the probability of the Q distribution by this. So this is really exactly the same thing we did. And of course, it's somehow nice. We know that the cross entropy works very well for generally a multi-class classification problem. So it's a very promising idea. The additional nice thing is that this is really directly connected to the Kueberg-Leiber divergence. So if we calculate the Kueberg-Leiber divergence, if you remember, it was P of X times log P from X divided by Q from X. Now you only have to do a little bit of math. Hopefully you still remember that the log of a quotient here is like minus and plus. And then you can put them separate. And then here you have exactly negative the loss we just had before, plus this one, which only depends on P, which is the entropy of the para-teachers network. So the nice thing is, this, of course, is independent of our training loss. So we're training our student. So this will stay constant all the time, which means if we are minimizing the cross entropy, we are also minimizing the distance between them. So we are keeping these two the same in the way that by optimizing the one, we are also optimizing the others. As for here, other cases, of course, we again can use different types of losses. I mean, another thing which is used, not surprisingly, we have two vectors. You can also, instead of probability distributions, you can also view that as two vectors, and they have the same dimension, so it's very easy to measure the difference. You can take something like the L2 norm and just take the difference between both of them and use them to minimize that. Both of them are used, and yeah, it depends a bit on what is better for your case. But you can either use a cross entropy loss, or you can use just the L2 norm between the two vectors. In both cases, you're minimizing the difference between both of them, and then making the predictions more similar to what we had before. So the important summary is that in the response-based knowledge distillation, we're only making use of the final output. That has a big advantage that we're independent of any architectural choices that we are doing in there. So, or not any, that's not true. The number of classes is fixed, but how you model your network is really independent of that. However, the disadvantage is if you're more free, of course, it also like you can get distill less knowledge from it. So we are not using any intermediate representation. So you're not learning how the model, you're not using how the teacher model gets from the input to this output probability and use that also as a signal. But you just like only use a final signal. So the question is, can you also use that? And I mentioned already at the beginning, this is possible, and that is what is then called feature-based knowledge distillation, where the idea is that we are not only computing similarity at the end here between our output probabilities, but we are also looking at the networks. So we're also trying to make the predictions as similar as possible in order to make similar types of prediction. And the first thing you can now do is, of course, you somehow take your hidden activations and compare them. So you make these hidden activations as similar as possible. Does anybody see a problem with this? Why this could be a bit challenging at some point? Yes?
The teacher has much more activation than that, right? That's more in layers.
That is one thing, yes. So you have more layers, so you have to somehow find an alignment. So like that, maybe not like first layers compared to the first layer, but maybe the third layer of your student network gets compared to the 10th layer of your teacher network. So somehow assuming then, yeah, the first 3 layers of the student network should approximate what the teacher network does in 10 layers. Of course, it's like a bit of an approximation, might not be perfect. That is one challenge. There is one very similar challenge also there. It's also a bit about alignment. Yes? So that might be that the dimensions are also different. I mean, of course, it's easy if they both have the same dimensions. But then, of course, you're a bit limited on reducing the size. So that means your student network has to have the same width as your teacher network. You can only reduce the number of layers, but the size has to be the same. If you want to also reduce the dimension of the layers, things get a bit more complicated. But there is work, so now you can do that. The easiest thing is, okay, we're just also learning a mapping between the student and the teacher network, which of course comes again of the cost, but then we're trying to minimize the difference between the mapped student network and the teacher network. So that is here. So if we want to compare some hidden layer HS from the student with some hidden layer HT, we can't maybe directly do that. But if, I mean, it also doesn't make sense. If you once have a dimension of 100 hidden units and there you have 500 hidden units, then how do you compare them? I mean, there's no easy way. So what you're trying to do here is, can I learn some type of mapping that is easy to predict the target network? If we have here, if we can do that, then these representations have a good aligned. So then the most informations are in the student network. If you can, based on the student output, predict the target network, then most of the information are in there, and it's a good starting point. So you're minimizing the loss, and you're training like one additional layer mainly to map your student network to the teacher network and see if this is possible. If there are a lot less information in the student network, then of course you cannot do this prediction, and you'll always have, independent of what your WH here is, you always have a high loss. If most informations are in there, you can predict this, and then you have similar information in there. So this is like the two challenges when we want to directly compare some type of hidden representations. First of all, of course, we need the same layers. We can't compare a hidden activation of a transformer to one over LSTM easily. But secondly, we need to align the layers. If we think of a large network, so we have to say that maybe layer 5 is similar to layer 7 or so. And then we might need to realign them or re-estimate them in order to do that. So this is the one way in feature-based knowledge that we try to directly compare the hidden activations. So we directly want to know and want to have them as similar as possible. Of course, that's a very strict thing. So you're really like forcing the student then to really exactly do what the teacher does. It's not like it doesn't have to, it's not allowed to find his own solutions, but it should be like it's very strongly supervised, because it's like you always do first this step, then do that step, and so on. Another way is to measure at each of the steps a bit, like at what information are you looking at. So that is another way of looking at feature-based knowledge, is to look which of the input is currently important. And the idea is that it should be a bit similar. So in the layers, the student and the teacher network should somehow look at similar information of the network. So if we want to do a classification of images, if the network is classifying a dog, it should maybe look at the head of it. And so the network, both the student and the teacher network, should be looking at the face of the dog and should be mostly focusing on that. And can we compare that? Or if you think about a text-based system, we have the attention metrics, and you want that maybe for generating the next token, it should look at which tokens are important and focus on the same ones before. Yes?
So on the slide that says output, but do you mean input or
that is a good point. Yes, I mean input. Thanks for correcting that. Yes, I'll try to correct it later. So yeah, you look at which input is important for which one. So how can we do that? We want to, I mean, there are a bit of different techniques typically are used for that in vision and in NLP. So we want to look at both of them and see a bit that you get an idea of how you can measure the import. A lot of vision-based models are like having the typically CNN, TDNN architecture. So you do this convolution over it, and then you have a lot of channels. So in one layer, you mainly have a hidden size for each region, or you can even say it if you have it like your original image is H times W, so height times width. Then for each of the image point, you have a vector of times C. So typically we're not talking about hidden size then, but about channel size, representing, okay, what are the information at this? And it not only takes a pixel, but if it's like a CNN, it takes a region around it. And if it's like a visual transformer, it even takes a whole image. But in the end, you have the activation in each of the layers typically is that you have this C times H times W. So if you do something with images, before you're doing pooling, you typically have this activation where the activation is the channel size or the hidden size times height and weight in there. And the spatial attention map is now, can we somehow summarize all the different channels? So all the information we have about the current position into like one number saying how important the current pixel is, or like how much activation is there for the current region. So what we want to do is like you want to have a function which takes all the takes the current activation and maps it into a two-dimensional thing, which is only the image size, so that you can mainly say, oh, for the current hidden layer, most importantly are these pixels of the original image, because there in the hidden size there's most activation currently happening. I hope I not see only question marks. Any question to this general concept of this spatial attention map? Luckily, there's a very easy way of doing that, which is often done, which is, okay, we just sum up for the current pixel, we sum up all the activations of all the channels. So if you have these 3D hidden size, so you have here like height times width times channels. So it's a bit, so if we talked about language, we always had word, and for each word a hidden size. Here we have a channel size for each pixel, and then we are summarizing them up and get these attention map here, the spatial. So you just sum over this one up and you get that. And this somehow says, I mean, the motivation behind is, we just said, is that it is like saying like how much activation, how much focus is there on the different regions. So for each pixel, you get now a value telling you, yeah, how active the network is. And the idea is if the network is very active, this is somehow very important for the classification. Which of course makes sense if you think about pooling, you take later the maxer. So these are the regions which have most influence on that. So then the next step is not too complicated anymore. If we're having this, we can now compare these spatial activation maps for different networks. We have some limitations, so our network size should still have some of a representation for each pixel. So it has to be H times W, but the C size is no longer, it doesn't matter. So if the teacher network has a lot larger C than the student network, this is completely fine. So it doesn't matter how large your student network is. What we're doing is exactly, we're taking now this values we had before, this summed values here for each pixel, divided it by the sum of all pixels to get a relative attention, like somehow where like this is 1% of the overall, this is 5%, and so on. And then we're doing the difference between the student and the teacher network. And by this difference, we can now say, okay, if the teacher network mainly looks at the face, the student should also mainly look at the face. If the student network mainly looks at the teacher network, mainly looks at the ball, there should also the student network. And then we can have things like that. So here you have the teacher network where you have 3 groups of each one 3 layers. And the student network also has 3 groups, but only 2 layers each. And here you always do your attention-based loss, telling you that in this area, it should look at the same thing. So for CNN-based layers where you have, or also visual transformer, where you have like one representation for each pixel, you said that here. So you have a hidden representation or different channels for each pixel. You can compare them by looking at the attention metrics and try to make them as similar as possible. Any questions to this idea? And then we are here having mainly again an L2 loss. So you see, if if you want to compare things, L2 loss is important. And what you, I mean, the size is now the same. That is a nice thing, because both of them, we have a map of like height times weight, and this is independent of your size of the network then. Any questions to that? Good. Then we can look at a different type of models, and there is also attention is in there, but attention is a bit understood differently. And but you can do their very similar like comparison. So if we are talking about NLP, we typically mean the attention in either self-attention or cross-attention, and it can be also visualized. So this tells us like how important different words are for other words. So if you have self-attention, you see you have the sentence here twice, and then you have highlighted like where does the word look like. So if we're intending, if we're doing self-attention and we are comparing, then we are looking from farther, how are the others and how does it get attended and so on. So thereby you can measure how important different words were to understand other words. As a remembering, how did it work? So we have the self-attention. If you remember this type of network, so we do the query key value for all the words. Then we are comparing the query of the, here are we doing it for the second word here. So we are comparing the query to all the keys and getting here the attention value by then also doing a softmax. And these values are the ones which we are comparing in the metrics. So afterwards, you're multiplying these values by the value, and then that is your summation, that's your output. But this value tells you how much information you put in from each of the tokens into the final. So you calculate in order to calculate the new hidden state, how much information do you take from each of them? This is again a probability distribution. And that you're doing for each token, and that's why you get this metrics. For each time you calculate all the similarities to father, get a probability distribution, then all the ones to this one and so on. And that makes you giving like n probability distribution here, or the whole matrix here, saying how important each word are to each other. Yes, can you remember? Okay, yes?
What attention did we use before?
Here, yeah, this was what they call this spatial attention map. This is just the sum of all the hidden activation. That's why I said a bit careful. So this is what is referred to in this way of, in this work on attention, and it's different. So this network doesn't have self-attention. So it's not like a transformer, it's a purely CNN-based work. But in the CNN, you can say that the CNN or the overall network attends to something more by looking how active they are. But it's not what we call as an architecture the attention. So we have to be a bit careful here with the naming. Problem of work happens in parallel. People say, oh, this network mainly focuses on there, so they call it attention, but it's not what is referred to as the self-attention based network. So here we also have this, like, I mean, here you get very naturally how important some inputs are to some output. That is the whole idea of the attention. And this we can use again as an additional loss, which was here in some way of distilling BERT models. What we now can do is we can calculate the attention matrix for both models, and then we can again just do the minimum squared error of the two attention-based metrics. The nice thing is here again, the attention score is one score for each pair of tokens, so it's independent of the hidden size. So one transformer has a hidden size of 500 and the other one has a hidden size of 128. It still works because this only depends on your number of words, and you're doing it for the same input, so it should be the same. Now you should ask me a question. If you look at the formula, I said it's independent of the hidden size. Yes? Yes. Can you answer it directly? Do you know? Maybe I tricked you a bit with H. H can mean different things. Do you have an idea?
Or I thought it might be that we sum up for each of them networks, but maybe then.
No, this is something, I mean, you have the sum and you put there the attention matrix of the student and the teacher and are both of I. So it's right that it could be, but there is already an idea. Yeah. Yes, exactly. So this is not the hidden size, but if you remember, I know it's a bit, what we typically do is now we're doing not one attention, but we're doing like 8 in parallel or so, and that we call heads. So you do like the attention once, and then you do it 2 and 3 times so that you can attend on different things, which means you get 8 different attention matrices. So for each head looks at different words, so you get a different thing. So that's, of course, then an important restriction here. So you need the same number of attention heads, or you need some type of alignment again, which attention head to align to which one. But that one, I mean, if you do different types of attention, of course, then you need to have the same number. But yeah, I mean, it's a bit related to the hidden size because typically, of course, you split your full hidden size into 8 blocks if you have 8 attention heads. So it's related, but I mean, each block could be bigger. Any more questions to this? Yes.
I don't really understand how I think it means that our like the heads can be different sizes, right? From inside.
You know, in this case, they can't be. I mean, then you cannot calculate that because, as you're currently saying, I mean, you take the both say matrices, you have the same number of matrices. So you either have to like restrict yourself to have the same number of heads, and then you can only have smaller hidden size for each head, or you have to do some type of alignment and like say, okay, you randomly select or something like that. Yeah, so that's a very important thing to consider here. Good. This is the methods we looked at feature-based learning. Any more questions to that? Good. Then for the last part, we wanted to look at one example of what people refer to as relation-based learning. And the idea is that we want to now do a bit of an additional layer in between. So we want to look what are the relations between 2 layers, or like we have 2 layers from the one network and 2 layers from the other network, and try to have the same type of relation. So you see already, even like in general, the loss gets more complicated. So before we somehow did the loss based on one feature from the teacher and one feature layer from the student. So it could be like either like the attention matrix or directly the activations and so on. Now we are doing here, we're measuring the difference between 2 feature layers from the teacher and 2 feature layers from the student. And then we are, based on this like measurement or distance between them, we are then calculating a loss between the distance. So you can view it a bit like a distance between distances. If you want that, if you look what happens in the one network, you want that something similar happens in the other network. How does that work? What we therefore need to do is we compare different layers and measure the difference in there. So what you can see here is again, so we have here a similar setup that's from vision with like a feature map in the lowest layer and in the uppermost layer. And in each layer here, we have one hidden representation for each pixel. So again, you have like in the lowest layer here, you have like an activation, which is height times the width times C for channel, for example, here. And here we have M channels in the lower, and we have N channels in the top layer. And now the question is, can we learn like what really happens between these challenges? And what we are measuring there is this FSP matrix, this flow of information, which says which information are flown from the M channel here to the N channel here. So we are getting a matrix which has dimension N cross M. So the hidden size here and the hidden size. And what we're doing here is then again, we are just summing over all positions and multiplying the activation of channel E with channel J on the other thing. So like, how are the correlated these types of information on some hidden value in the lower layer to another hidden layer in the upper layer? And we're averaging that over all positions. So you want to somehow know how strong are they correlated, these two hidden layers. And yeah, so this is this G matrix, and which is first, I mean, this is now only done for one model. Then we have to compare these G matrices later. But first is this idea a bit clear. So you mainly, if you think about your hidden representation here, you have pixel like height and weight. So somewhere in your picture you are, and for each picture value, you have a lot of hidden states there, hidden dimensions. And now you're looking the third hidden dimension, how similar is it to the fifth and to the fourth and to the third hidden dimension? And then you're doing that by looking at each pixel on these two hidden representations and comparing each of them that you're doing here. So you're summing over your height. You're summing over your weight. So you're averaging out in the end over all possible pixels. And then you're always multiplying the value of E and J, and that gives you value E and J in your final matrix here. That's saying mainly the hidden layer or the hidden state 3 in the lower layer and the hidden state 5 in the upper layer, how similar they are, is measured in the matrix 3, 5, in the entries 3, 5 of your matrix. And once you have that, now you can, for these matrices, you can again build the differences between them and try to minimize them. So you're saying that these matrix values should be the same for your teacher and your student network. There's now one important thing. We have here N and M, so the channel size. So that, of course, is only possible if you have the same hidden dimension of both models. So you mainly can only do that if you have different number of layers. So you can only reduce your layers, and that's exactly what he has done. So here they are doing five layers, and here only 2, and then they are comparing and trying to predict them. So mainly saying these 5 layers should do roughly the same thing as these 2 layers here. And then here again, these 2 layers should do the same as these 5 layers here. And these 2 layers should do the same as these 5 layers here. And of course, at these positions here, between them, where you compare, the hidden size has to be the same. So the number of channels in vision words spoken has to be the same. Any questions to this? Good. So now we have done this for multi-class classification. For the last 15 minutes, we want to now see if there's, or a bit look what is happening in another type of models, and that is autoregressive models. Does anybody remember how we refer to, or to what we refer to as autoregressive models? Yes?
Models that take their own output as an input for the next iteration.
what were the typical use case, or where is it typically applied? Yeah, language models, we had even two types of architecture that are typically used. One is this encoder-decoder models. So where you have one encoder which reads, for example, the question and then generates the answer in the decoder. And the decoder part of that was an autoregressive model. And so someone need to connect those by cross-attention or so. Then you read where is culture, you process it, and then you generate word by word here. The answer is in German. The other way is like the other typically, so these are the two typical things for autoregressive thing is it's purely decoder-based models where you with the same decoder also in a more autoregressive model would read in the input, but for the input you force it to not like take the next your predicted token from it, but what is your input? So you're not predicting really what should be the next word after is, but you just force it the next input is Karlsruhe, and then you start generating in an autoregressive model. So this is how typically a neural network, a large language model looks like. And if we are training that, then we also had this table a bit how we're training it. So we can do that with cross entropy. So we are putting here our sentence. We are putting it through the correct answer here. We're putting it through it. And then we are predicting the labels. We are always checking. So here we should predict these and calculating then our cross entropy. So we are not like having one feedback signal, like for this is the correct label, but for each position of the decoder, we are predicting what is the correct one. And we can do that in parallel because we know what the answer is. That is our label. So we put our label here in and then predicting the correct answer. So of course, now if you think about large language models, you have a similar problem. You also want to do the same thing. You want to do knowledge distillation. So you want to do you train a small language model based on your large language model and do a bit the same. You can also do the classification loss. So first of all, it seems to be a very good idea to do something similar, to do also this type of knowledge distillation, also for autoregressive models as we had before. We can just calculate the loss based on the output. We can calculate the loss based on the distillation loss, and then like try to make the model predict exactly the same thing. However, there's one challenge. Does anybody see this already? Yes?
Because this neural network is typically focused in the deep network, I guess that after like new calculations, the output of this neural network is getting worse and worse.
Going exactly in the right direction. What are the previous outputs is important, but it's even not so important about the student and the teacher network. There's one other thing which is even more important in this case, because we're calculating these two losses. So it has to be the same generation by the label and the teacher network. And that, of course, is not always the case. Why is this the case? So maybe it gets clearer. So if we're doing our training, what we do in normal cross-entropy training, we put the label sequence here. We pretend we know what is correct, what it should generate, and put it all here. And then we're generating and calculating the loss here, which is now the correct solution. So here should be dies, here is, and here is ein, and so on. But we are not really doing the generation. So in training, we are telling the model, this should be the input, and then we're just doing the prediction. Because otherwise, we wouldn't even know what the correct information is. If the model is predicting here das, so then if we would like tell the model, no, you should predict these, but currently you predict das. If we would have put das in here, it's no longer clear what is the right answer. So we only know the right answer for this sequence of decision. For any other sequence of decision, we don't know the right answer. That is why we only can train with the correct sequence here. And the other sequence, we have to, hopefully learn that the model will always then go in the similar. So what is now the problem is, now here we're getting two signals. We get the signal from the output. The output of the label is the correct sequence that we have in our training data. And we get the label from the teacher network. Of course, the teacher network is relatively good, but that doesn't mean that the sequence is the same. So it can be that the teacher, when we would just generate now an output, would generate a complete different sequence. And then it's not clear how to train. Should we now put in here our sequence from the student, from the labels, or should we put this the teacher's sequence in there? So the correct one, which is in your training data, or the one which is generated by the teacher. It's not clear which one to put here, and you cannot in parallel put both of them in there. Yes?
But was it not exactly the thing that we are looking at the output probabilities, and so we can just for the like if you don't look at the whole sequence but only at the next word, and the teacher predicts something other than the actual output would be, then we could just I don't know give credit to both, because the teacher already knows that has a bad idea. Like the teacher network probably has ideas for which words are bad and which are good and which are a little bit good, a little bit bad, and we can use all that.
Yeah, but I mean, that is the idea. But the main challenge is at the next step, you have to decide which one you put in here. And you can either decide for the teacher or you can decide for the student. But you cannot like easily do both. I mean, maybe we can just run it twice, but it's no longer as easy as before, and we can just have different predictions. So if we have autoregressive, we have to decide which one we took here. And if we take the teacher, we are not directly knowing what is the correct label, because we don't have correct labels for that. And if we take the correct label, we might not directly know the student. So we have to a bit adapt our strategies. And there's like 3 ways of doing that. The first one is related to that. So what you're doing, and that is referred to as word level knowledge distillation. So what that means is we're not really generating a translation by the teacher network. We are only generating the probabilities. So we are forcing the teachers to do exactly the same thing as a label. So the teacher is not really generating an output. It's just like evaluating how probable the output is. So we are, as in training, we are not generating tokens, but we are putting the full tokens here and then calculating the probabilities. So we are not using the teacher model really to generate a sequence, which might be different, but we are only using it to calculate output probabilities for the full sequence of tokens. And then of course it's nice, because now the sequence of the teacher and the sequence of the ground truth here is exactly the same. So what we can then do is we can again just take both probabilities and somehow combine them from the ground truth and from the labels. So because the sequences are not, we took the sequence of the teacher, of the label, so the ground truth sequence, and just use the teacher to give probabilities for each of the tokens. And then we can use them and use them in the same. Of course, it comes at the cost that we are now stick to the sequence in the label sequence. And we cannot use that maybe the teacher will give us, for example, the same output for the same input always, and we have more the similarity. This is no longer the case, because for the same output, it might be that we have different answers in your training data, and now we always use the training data examples and not the ones from the teacher network. Is this idea a bit clear? Or a lot of questions? Yeah.
So this like the question is like, do we decide for the teacher or the normal label to continue? Like
yes.
The word sequence in this case we completely decide on the labels.
Yes. Yes. Exactly. So there's 2 other ways. So you can also just decide on the teacher network and ignore the ground truth. So what you can do is, for example, then it might be not good to only take the most probable sequence, but you can generate some possible outputs by the teacher and use all of them. This is then, again, the idea is, okay, then we have maybe the correct one for always similar ones. So you heavily rely on the teacher network then, because there's no ground truth here anymore. So you're ignoring the ground truth. You only rely on what the teacher gives you. That's referred to as sequence level knowledge distillation, because now the whole sequence is generated by the teacher and not just like the word level information. This really gets now very similar to data augmentation, because what you mainly do is you take your input data, you let the teacher network process it, and use this synthetic data based on the teacher and generated by the teacher as your training data. So you're really not looking at all anymore at the ground truth. So this one here, the classification laws, is somehow completely ignored. You really only rely on this one, because which of course again comes as a cost. If then this is this is removed and you're only relying on that one, which of course is difficult. If your teacher is bad at something, you're completely ignoring that and not using. And this then of course comes with another way of trying to prevent that, and that is a sequence level interpolation. So where you try to integrate a bit the ground truth again, but still rely mainly on the teacher. And the idea is you generate some sequences by your teacher network. So these should all have high probability by the teacher. But then you not take all of them. Then you look at your ground truths, and you can then do a pre-selection and say, oh, these are all selected by the teacher. So I take the one which, according to some similarity metric, is the best matching, so that you have one which is least similar to your reference. So you see the most probable one is ACF. The ground truth is ECD, but then you say somehow, okay, ECE is most similar to that. So I train my student network on the one which is reachable by the teacher network. So that is a bit the idea. Maybe this one is just too complicated for the student network, so it's bad to learn that. So you take one which the teacher network at least can generate, and then you take the one which is most similar or the best one based on that. And you're not taking just all of them or the one which the teacher network says the best, but you're comparing it to the ground truth, thereby preventing that if the teacher model is like completely off, generating some crazy stuff, you're not ignoring that and don't use that. Good. Any more questions to knowledge distillation? Yes.
Maybe a more general question, but to me it's not really clear how the student networks are initialized. Like, do we are these completely new networks with possibly different architectures that we initialize randomly, or do we take the teacher network and just remove those networks?
I think the default thing is really start from scratch and training with a random initialization. So there could be another way of teaching that you try to like take some parts of the network as your starting point. But I think the standard thing is that you start with a random initialization, try to learn that, and only over the loss you try to have this bias to be as similar as possible. Good. I think then we're skip the rest. Maybe we're doing that next week on Thursday a bit. But just to summarize, because we're at the end of the lecture, so what you should remember is like the student-teacher setting, that you have a strong one model and a mostly weaker other model, and that should teach it. And then the most important thing is that we saw that the signal of how to teach is always via the loss. So we have to tell the model what is like good or wrong. We can do that on the output level. We can do it on the feature level, on the relation level. We've seen different ways of teaching that, but that is the important thing here. Any more questions? Yes?
What does AD for stand?
Knowledge distillation. Yes. Sorry, yes, I should have written that. Okay. Good, then thanks a lot and see you again on Thursday.